Rust memory management operates across two distinct territories. You have the ordered stack, where data sizes must be known perfectly in advance, and you have the dynamic, unstructured heap, used for data that grows and shifts at runtime. Standard references operate as mechanisms that borrow data. They point to an address and observe the value, but they never claim ownership of the underlying memory. This logic hits an architectural wall when a system requires multiple owners or shared mutable state on the heap. Because a standard reference cannot own what it points to, the compiler's strict safety rules reject these complex topologies. To bypass these constraints, Rust utilizes smart pointers. These structures act like references, but physically own the data they point to. These are standard structs, not compiler exceptions. They are armed with hidden metadata and traits that expand their capabilities beyond simple borrowing. We will deconstruct the three primary smart pointer patterns used to navigate these strict limits. First, the box smart pointer. Second, the RC tally pointer. And finally, the RefCell. Escaping the compiler's strict constraints is required for complex systems. However, moving past these boundaries transfers the burden of safety directly to the engineer's architecture. Box is the most direct smart pointer, designed to manage types whose exact size cannot be determined at compile time. Recursive structures, like a cons list containing its own type, pose a mathematical problem. The compiler cannot calculate stack space for an infinite sequence. A box fixes this by moving data to the heap, leaving only a fixed size pointer on the stack to manage the address. Wrapping data in a struct normally creates syntactic noise, forcing the developer to manually call wrapper methods to see the inner value. Rust resolves this through the deref trait. Using deref coercion, the compiler automatically follows a reference chain to access the inner data, allowing a smart pointer to behave like a standard reference. In languages with manual deallocation, heap management carried the risk of memory leaks or double free errors that could corrupt the entire system. Rust automates this cleanup through the drop trait. Drop acts as a destructor, executing custom cleanup code the moment a smart pointer goes out of scope. The cleanup is precise, tearing down nested structures in the exact reverse order of their creation. Box provides dynamic heap ownership, while deref and drop allow the struct to function with the ergonomics of a safe reference. Single ownership becomes impossible in architectures like UI component trees or document undo buffers, where multiple nodes must access the same state. If a profile widget and a settings menu both need to access a single user object, the system requires shared ownership. A standard box fails here. Transferring ownership to the settings menu would immediately invalidate the profile widget's pointer. The reference-counted smart pointer, or RC, provides the architectural solution for safe, simultaneous multiple ownership. Within the heap, the data is wrapped in an RC box, maintaining a running tally of active stack pointers. As stack variables go out of scope, the tally decrements. The heap memory is only cleared when that count hits exactly 0. This safety requires a compromise. To prevent data races, RC strictly enforces immutable access across every owner. RC enables architectures with shared lifespans, but it effectively freezes the shared data as read-only. Systemic roadblocks often appear when a developer needs to mutate state, but the external API strictly requires an immutable reference. This is common when creating mock objects for testing. The object must track messages internally while appearing immutable to the rest of the application. Because of the halting problem, the compiler is conservative. If it cannot definitively prove an operation is safe, it rejects the code, despite sound logic. RefCell and the concept of interior mutability bypass these limits. It presents a static, immutable outer shell to the compiler, while allowing the values inside that boundary to dynamically mutate. This creates an architectural trade-off, moving the strict borrow checker rules from compile time analysis into the runtime environment. Violating ownership rules at runtime triggers a panic, crashing the program instantly rather than providing a safe compiler warning. Interior mutability provides a deliberate deferral of verification, trading compile time safety for runtime flexibility. Nesting a RefCell inside an RC allows for complex, mutable graph nodes with multiple owners. However, this combination creates a vulnerability, the reference cycle memory leak. If box A is mutated to point at box B, and box B points back at A, they form a closed loop with a strong count of 2. When stack pointers vanish, counts drop to 1. The nodes are stranded in memory, completely unreachable. This is a deadlocked state. Box A cannot be dropped while Box B holds a reference to it, and Box B is waiting on Box A to release its own pointer. The memory is effectively lost, occupied and invisible to the rest of the program. To solve this, developers use weak pointers to separate structural ownership from passive observation. A weak pointer increments a secondary count that does not prevent the data from being destroyed when the strong owner count hits 0. Modern graph architectures require classifying these relationships, separating the owners of data from the observers to prevent systemic gridlock. These 3 smart pointers provide a definitive matrix of engineering choices for data architecture. Use Box for basic heap allocation, RC for shared read-only graphs, and RefCell when mutability is required behind an immutable interface. When using weak pointers, the engineer must call the upgrade method to verify the data still exists before attempting to access it. Rust's memory constraints function as a programmable feature space for the modern systems engineer, forcing developers to explicitly architect the lifecycle of their data for every memory address.